Double integrals are usually the first types of integrals a student will encounter in Calc 3. They certainly were for me, and while I had a fun time with the newfound notation associated with them, they are actually a very simple extension of single variable integrals under the hood. Take any arbitrary function f of x. From our Calc 1 class, we know that to find the signed area underneath the function, we must divide our domain into little segments of width dx, multiply each dx by the value of f of x somewhere above it to get a small piece of area, and add up all these tiny areas, taking the limit as the width of each interval approaches 0. Now extending this to the three-dimensional case is actually pretty natural. Take some 3D graph. The volume underneath this surface and above the xy plane can generally be given by this double integral, where a, b, c, and d aren't all necessarily constants. Pick some y, say y0, on the xy plane. If we draw a line parallel to the x-axis and find the cross-sectional area of the graph above it, we get that it's equal to this integral. To extend this to get the volume, imagine a cylinder. We know that the volume of said cylinder equals pi r squared, or in other words, the cross-sectional area times a length in the perpendicular direction. In a similar fashion, a little volume element for our 3D graph is given by the integral that gives us a cross-sectional area for some given y value times a little step in the perpendicular direction dy. Now when we integrate this a second time, with our bounds for y this time, we are adding up all these little volume elements to get the total volume, and it can be visualized by the cross-sectional area sweeping back and forth. This mental model can give us a little bit of intuition for Fubini's theorem, which tells us that we can switch the order of integration for sufficiently nice functions. It should make no difference whether we first take the cross-sectional area parallel to the x-axis and sweep along the y-axis, or first take the cross-sectional area parallel to the y-axis and sweep along the x-axis.
Yay!